So in case of single variable calculus, let me start with this one. Okay. Suppose f is a function of x. Okay. Let me take a continuous differentiable function. I hope you know about differentiable function. F of x, is that okay? A function of one variable. Okay. Let me take that one. Now, what does this df by dx? What does this gives? We write it as f dash of x. Okay, let me write it as f dash of x. More comfortable. What does it gives? Again, geometrically, it gives slope of the tangent drawn to that function at some point, isn't it? So that's a geometrical meaning. Other than that, again, what is the actual use of this one? Now look at here. So what you again, whenever you write a single variable function like this, f as a function of x, okay. Now we say x is independent variable, f depends on x, okay. We say like this, suppose f of x as a function of x, okay. So I have some function here. We say x is what you call independent variable, f of x, f which is depending on x. That's how we say. Is that okay? Where x is an independent variable, it's called as independent variable. Now, if I change that independent variable by a small amount dx, okay. So how does that f changes? Is that okay? Now, so this derivative will play the proportionality constant here. Is that okay? When you change this what you call independent variable by a very small amount, infinitesimal. Is that okay? By infinitesimal amount, okay. How does this this function changes? How much? What is the change of this function? So this one is f dash of x actually. Is that okay? Or you can write like this: df is equal to df of x by dx into dx. Is that okay? Or you can write like this: that's equal to slope. Am I right? Slope at that point. So slope at the point where you are so taking a small displacement. Okay. Small displacement means infinitesimal displacement. You can define a point over there. Okay. On x-axis. Slope into dx. You can write like this. Is that okay? In case of single variable calculus, this again, so derivative, it will act like a proportionality constant. If you change this variable, how much change in this variable? Is that okay? So I hope this is not a big deal for you. So it's a single variable calculus. Now look at here. In case of single variable calculus, okay, there is only one possible way of changing x, isn't it? You have to move like this, am I right? You have to move like this. So from this point, if you take a point on x-axis, you have to move like this, isn't it? To change x, there is only one way of changing x, isn't it? So suppose if you have two variable, three variable, so that's a different story actually. Let me try to code that one. Now I think you can move like this or like this, okay? So that's your choice. You can move along positive x-axis or negative x-axis. But other than that, other than moving along x-axis, you don't have any other choice, isn't it? So that's why to find the change in f, okay, or to change f, okay, you are moving in one axis, okay, one particular direction, isn't it? And you will find what is the change and all. Is that okay? Now look at here. See this expression again, okay? See this expression here. If this what you call again, let me take two cases here, okay? Let me take one curve like this. Let me take other curve like this, okay? Now if you do some dx here, okay? So dx here. So corresponding change in df, what is this one? Which is low, isn't it, here? This is f as a function of x, okay? F as a function of x. But if you change what you call x here by amount dx, okay? So change in f is large here, am I right? Actually, those should be infinitesimal. I have exaggerated them. Is that okay? Speak out. So that's why again, what is the difference here? So at this point your slope is low, at this point your slope is high, isn't it? You can observe that one. So that's why whenever that slope is high, okay, if you change this independent variable by small amount, okay, so this will change by large amount. Whenever slope is low, okay, if you change this one by a small amount, okay, so this will change by a small amount. So that's how it will act like a proportionality constant. Is that okay? You can take this idea. This is the best idea. Is that okay? Now you can say here at this point you have low slope is very low. That's why when you change x, f is changed by small amount. Okay. Here slope is high. When you change x, f is changed by large amount, isn't it? So usually this whatever this dx we write, okay, whatever this dx we write, okay, this length is infinitesimal and it is constant actually. We don't know what it is. We don't write that one in terms of centimeter, millimeter or something. But in calculus, we will take this one as a that value as a constant, okay, dx value as a constant actually. Infinitesimal and that is constant, okay. Speak out. So what I am saying is whatever dx you have taken here, I have exaggerated this one. I can't show this one. Okay, the same dx you are going to write here. Is that okay? Wherever you write this dx in case of calculus, okay, you believe that what you call, so this is what you call constant, okay. This length is constant. Is that okay? That's how you are going to imagine. Is that okay? So one suppose while discussing one graph, you take one value of dx. While discussing other graph, you take other value of no, not like that. In calculus, everywhere this dx, this length is same, infinitesimal and same. Is that okay? Speak out. I hope you can grab this point. Okay. X is independent variable. That's how we say x is independent variable, but that length dx, it is always same. That's how we believe. Whenever we compare, look at here, I'm comparing here, am I right? When you compare, so this dx, whatever you take, that remains same. So then if this is constant, okay, if this is constant, then what does this change in f depends on? That depends on slope, isn't it? Is that okay? So that plays a kind of proportionality factor actually, okay. I hope you can grab it. And one more thing you already know. So this is nothing but slope, am I right? That's equal to, so slope of the tangent, so drawn at that point where we take the derivative. And one more thing you need to observe here, because later I'm going to convert all of this to what you call so multivariable, okay. This derivative, okay, this derivative is a point operation. What do you mean by point operation? You are going to take derivative at some point, isn't it? So again, if I take some point x naught here, is that okay? If I take some point x naught here, you are going to take derivative at x naught, isn't it? Slope of the tangent at that point, am I right? You can take df by dx. We are going to write as f dash of x, isn't it? You can have f dash of x naught, am I right? Or df by dx at x naught, am I right? So that's why that derivative is a point operation. Can I say like this? You are going to take derivative at some point. Here at some point along x-axis actually, you are going to choose a point on x-axis and you are going to take the derivative, isn't it? And that's a point variable also, you can say like this, isn't it? That's a point variable. After taking derivative, it's again function of x, am I right? At different x value, it has a different derivative, isn't it? Derivative is a point variable. Or you can say derivative is a point operation, am I right? You are going to do that operation at some point on x-axis, isn't it? By choosing a point on x-axis, isn't it? Speak out, okay? You need to observe all of these because these can be generalized to 3 dimension, okay? So this is in case of single variable calculus. Is that okay? Any questions? Speak out. So shall I move on?
Sir?
Yes.
Sir?
Yes.
So we get to that, so we get to that derivative is the rate of change at the single point.
Yes. That's what this says. Suppose if you take derivative as a function, so that gives what you call, so general value, isn't it? I mean, So you can use this one, isn't it? You can use that function. You can have the derivative at any point, isn't it? But usually, derivative of a function, that means slope of the tangent drawn at one point, isn't it? That means you are choosing one point on x-axis and you are taking derivative, and you will get some value, isn't it? You will get some number, isn't it? Yeah, speak out. Now let me. Slope is rate of change at that point, actually. Again, for this you have to do one thing. I mean, to understand this derivative clearly, you go through Essential Calculus by James Stewart. Okay, at the starting, he has started with that Galileo experiment. If he drops a ball from some height, okay, so then its displacement will be some 4.9 into t square, g by 2. So then he asked the question, what is the velocity exactly at 5 seconds after you drop? What is the speed exactly at 5 seconds? Starting from average speed, they go to instantaneous speed. There again that will become a limit actually. Mathematically, that instantaneous speed, that will become a limit actually, limit of s of t2 minus s of t1, like that. Okay, so that's the best idea to understand how that calculus idea came. Is that okay? Let me share that. Now let me go for multivariable. Is that okay? Suppose I have a what you call scalar field. That's what I defined, isn't it? What do you mean by field? Field means it's a quantity which takes different value at different point in space. That's called as field. There are two kinds of field that we define. One is scalar field, other one is vector field. Am I right? Our electric field and magnetic fields are vector field. Okay. Suppose if we take a temperature of this room, okay, then that will be a scalar field, isn't it? Now let me take that kind of scalar field, which is a function of three variables, x, y, z, and it may be possibly depending on time. I'll not take time variable right now here. Okay, later I'll take time variable. Is that okay? Now look at here. Suppose you can imagine like this. We have a room here. Okay, I put a fire here. Is that okay? Then temperature at a different point will be different. Am I right? Right now, maybe temperature may be same at almost all point of this room. Suppose if I put a fire at one corner of the room, then nearby that fire you will have higher temperature. If you go away from that fire, you will have low temperature, isn't it? Then temperature will be function of x, y, z. Am I right? You can choose some coordinate. Is that okay? Now let me take like this. Okay, I have a room, cubicle one. Okay, I have a room. So I what I do is, again I have to choose a coordinate also. Am I right? I have to choose coordinate system also. I'll take this one as x, this one as y, this one as z, this one as origin. Okay. Now I'm going to put a fire here. I'm going to put a fire here so that you can define temperature at some point. Am I right? T, x, y, z. Okay. At point P, x, y, z, isn't it? You can define a temperature, isn't it? We call that one a scalar field. Why that's a scalar field? Because it will add like a scalar. Suppose if you put two fires, okay, if you find temperature due to individual fire, then net temperature, when you keep both fire, it's going to add like a scalar. You don't have to pick out any direction, isn't it? Suppose if you put one fire here, other fire here, okay, find the temperature at this point due to this fire, find the temperature at this point due to this fire only, okay. Then when you keep both fire, temperature at this point, which is a scalar addition, just addition, isn't it? That's how, again, we defined vector and scalars like that only, isn't it? Using their, what are the rules that they follow while adding, isn't it? So remember that point. Now let me take that one. So let me take a temperature here, okay, let me erase this point P. Now from this point, okay, I have to change x, y, z, isn't it? To change t, I have to change x, y, z, isn't it? Now from this point, again, in what direction you can move? You can move in infinitely many directions, am I right? From a point in space, you can move in infinitely many directions, isn't it? So in case of single variable calculus, what happened is, if you want to change f, you are going to change x. That's it, isn't it? That means you are going to move along x-axis. Are you getting the point? In case of single variable calculus. So now this is a 3 variable function. We call x, y, z are independent variable, t depending on x, y, z. That's how we say. Okay. Now you can change x, you can change y, you can change z. Okay. You can change all 3 together, isn't it? So again, as a result, look at here. In case of 3 dimension, okay, you can move in any direction. Am I right? You got infinitely many direction to move from this point to next neighboring point. Can I say like this? To move from this point to next neighboring point, you got infinitely many ways. In case of single variable calculus, to move from this point to neighboring point, you usually move along x-axis. Only one possible way, isn't it? Only x-axis. Is that okay? Speak out. Now look at here. Wait a second. Let me conclude. So again, you found a derivative df by dx, isn't it? What is this derivative? Again, when you move along x-axis, when you change x by infinitesimal amount, so how much f changes and all, rate of change, am I right? Isn't it? You found that df by dx. But here, you can move in an infinitely many direction, isn't it? And if you move in one particular direction, okay, if you move in one particular direction, let me take the displacement as dl, the displacement vector. Now I have to define a vector. Here I don't have to write dx as a vector, am I right? Are you getting my point? Here I don't have to write dx as a vector because only one dimension, isn't it, that you can move. But here you can move in infinitely many directions. Then I have to define my infinitesimal displacement or infinitesimal change as a vector, isn't it? Now let me take so again this displacement as a infinitesimal displacement vector. Again, you can write this one as again dx into x cap plus dy into y cap plus dz into z cap. Okay. Usually this mod dl, as I told, this dx length is constant. Am I right? In the similar manner, here this mod dl, this length is constant actually. In calculus, this length is constant. Now look at here. So here you had only one way of changing x, okay? Only one way of changing f, I can say like that, am I right? But here you have infinitely many ways, isn't it? You can move in this direction, you can move in this direction, you can move in this direction, you can move downward, vertically, upward, horizontal, isn't it? Now, what is the rate of change of this temperature? Okay, when you move in this direction, what is the rate of change of temperature when you move in this direction? What is the rate of change of temperature when you move in this direction? When you move downward, when you move upward, when you move horizontally, isn't it? What is the rate of change of temperature? So that's the question. Here you have only one rate of change, isn't it? Look at here. Here infinitely many rate of change comes because you can move from that point to neighboring point in infinitely many ways, isn't it? Are you getting my point? Look at the situation that we are in. We are in the situation where we may need to define infinitely many derivatives, isn't it? To find the change, we may need to define infinitely many derivatives, because so if you move in a different direction, it is giving the when you again you can take this idea only. When you move this diagonally away, usually your temperature will change in a large extent. Am I right? The rate of change of temperature will be large. If you move away from that fire, okay, your rate of change of temperature will be large, isn't it? If you move if you move towards that fire, your rate of so temperature will increase. Am I right? Suppose if you have a fire here, suppose if I have a fire here, okay, so then I will move like this. So perpendicular to radial direction, okay, then usually rate of change of temperature will be low, isn't it? If you move in one particular direction, rate of change of temperature will be high. If you move in other particular direction, rate of change of temperature may be different, isn't it? So that's why different direction, if you move in a different direction, rate of change of temperature will be different. And how many directions that you can move? Infinitely many. Will you define derivative for each of those directions? Then you may need to define infinitely many derivatives. Are you getting my point? This is the problem in case of multivariable calculus. But here, define only one derivative. Okay? Then if you want to find change in f because of change in x, you just put the derivative. Is that okay? Are you getting my point? So here, if you want to find change in t, let me write dt, change in t, isn't it? Now again, you have to put some, so can I write t dash, just like you write f dash here, so derivative, and dl vector, let me put mod here, is that okay? Now again, for each and every direction, will you define this derivative or rate of change? This is the rate of change, let me say rate of change. Okay, we are in the situation where we may need to define rate of change for each particular direction. How many directions you can move? Infinitely many, isn't it? So that's the situation that we are. Yeah, your question. I think you forgot. Yeah, so any other questions? We go.
What's the better convenient in one direction, two direction, three direction, or multi-direction? If I will put the fire in X direction, it will obviously.
No. In case of again, if you put a fire here, temperature is a 3-variable function. It cannot be 1-variable function, isn't it? If you take some other example, so for 1-variable function, suppose a body moving in one direction like that, velocity like that, so position as a function of time, like that you have to take. Yeah, speak out.
So here DL is like of any position vector type, sir.
Infinitesimal displacement from that point. So here also you have taken infinitesimal displacement, isn't it? To check how fast f is changing, isn't it? So similar to that dx, we define dl, but it's a vector now. Here it need not be vector because it's a one dimension, am I right? In case of one dimension, you don't define a vector, you define a variable.
No, sir. My question is.
Wait.
So we can say that it is like of position vector, sir. DL.
It's not position vector. Position vector is a vector from origin to that point. So this is an infinitesimal vector from this point of interest. Let me take point of interest. dl vector whose length is infinitely small, like dx. Dx you are going to define here, am I right? Like that, this displacement vector you are going to define in space, not from origin to that point. Okay? Be careful. Yeah.
Question is, if I will go in the X direction, then how do I sense in the Y direction of the temperature? Because temperature is all over the 3 direction, right? If I will go in X direction, then how do I measure?
You don't say temperature changes in y direction, x direction or something. It's a scalar quantity. You just say temperature changes. In this case, if you move along x-axis, temperature changes. That's how you say.
Then the sense will be same in some region. If I will go in the X direction, Y direction will be same.
No, what do you mean? Again, if you move along x direction, how can you talk about y direction change? Tell me. If you move along x direction, that means you are keeping x plus dx, am I right? Comma y naught z naught. You are keeping y and z variable constant, isn't it? Yeah, speak up. Yes, let me move on.
Sir,
Yes.
sir, that T prime is the rate of change of.
So temperature with respect to distance only. With respect to distance. Yeah.
Rate of change is used with respect to time, sir.
No. This is rate of change. Okay, that's a good question. Why I use this rate of change? Whenever you say rate, then so that's with respect to time, isn't it? That's a very good question. It's not rate of change with respect to time, okay? Rate of change with respect to displacement only, okay? with respect to distance only, okay?
Space.
Hmm?
Space.
Or you better write rate of change with respect to displacement, okay? Yeah, derivative is called as rate of change, am I right? But rate of change with respect to what? Sometimes we just say rate of change without quoting anything. That is usually with respect to time, am I right? I'm not talking about time here, okay? I'm talking about space only. So am I right or not? Sometimes we can call it rate of change. We don't quote with respect to. Can I call this one as rate of change? With respect to x actually. Speak out.
Amount of cell is
F dash of x, can I call it as rate of change of f with respect to x? We don't say that with respect to usually, sometimes, isn't it? That's correct. Sometimes, again, most of the case, we use that rate of change word for derivative with respect to time actually. Okay, but here I am talking about space here, not time. Is that okay?
Yes.
Speak up.
Yes, sir. Yeah, rate of change with respect to space, sir.
Yeah, again, so I mean, in calculus book, do we call this one as a rate of change or not? Tell me.
Sir, we can't say only rate of change. We have to show with respect to.
Again, we said rate of change of f with respect to x. That's correct. Okay. So this is also rate of change of temperature with respect to displacement only. Okay. I'm not talking about time here. Is that okay? That's a good question. Yes. Now look at here. We are in the position to define infinitely many derivative, because if you move in different direction, you make a different rate of change with respect to displacement, isn't it? So, but calculus is very kind for us again. Is that okay? So, in calculus, if t is a function of x, y and z, I think we can define dt, just like you again in case of what you call a single variable calculus, you define df is equal to df by dx into dx, am I right? So, define like this, okay? Similarly, you can define dt as dou t by dou x into dx plus dou t by dou y into dy, okay, plus dou t by dou z into dz, isn't it? You can define like this. You can define like this. You can define this one. Is that okay? If you move in any particular direction, okay, you will change x, y, z, isn't it? You are going to change x, y, z. Suppose if you move only along x-axis, dy and dz will be 0, isn't it? Then you can take this part like that. So I have taken temperature as one of the example. Okay, this can be any scalar field. So this can be any scalar field. Now look at here. You can move in any direction. If you move in any arbitrary direction, x, y, z will change. Okay, you take infinitesimal change in x, y, z, and you take the partial derivative. I hope you know this symbol. Okay, partial derivatives. Okay, dou t by dou x, partial derivative of t with respect to x, partial derivative of t with respect to y, partial derivative of t with respect to z. What do you mean by that? You have to keep other variable constant. Am I right? While taking partial derivative of t with respect to x, you have to take y and z constant, isn't it? I hope you know that one. Now what we do is, since we are displacing in one particular direction, okay, where that infinitesimal displacement vector is written as dx into x cap plus dy into y cap plus dz into z cap, okay, isn't it? Now what we do is, we are going to rewrite this expression, okay, in case of Cartesian coordinate. In case of Cartesian coordinate, we are going to rewrite this expression like this. Look at here. Dou t by dou x into x cap plus dou t by dou y into y cap plus, calculus is allergic to you, dou t by dou z into z cap, isn't it? we take dot product with, okay, dx into x cap plus dy into y cap plus dz into z cap. Because we wish to find the derivative when we move in a particular direction, am I right? When you move in a different direction, we want to find derivative or how that quantity changes, am I right? Rate of change. Let me say take rate of change only, okay, word, but rate of change means I mean with respect to space only, okay? Rate of change, if I say rate of change with respect to space only, there is no time variable here. Is that okay? Yeah. So because our application is to space, electric field and magnetic field, spatial variable usually, okay?
Or you can say like that, sense of temperature with respect to X. Sense of temperature
With respect to, again, with respect to some displacement actually, with respect to some mod of displacement. That's the meaning, isn't it? Mod of dl, with respect to mod of dl, like that, okay? Now look at it. This expression I'm going to write like this. I hope you can deal with this dot product. Speak out. X dot x cap dot x cap, dou t by dou x into dx, dou t by dou y into dy, dou t by dou z into dz. We are going to rewrite this one. Is that okay? Because we want to find rate of change, okay? We want to find rate of change, rate of change or rate of increase, okay? We want to find rate of change, okay, in some particular direction, isn't it? That's why I'm going to rewrite this expression like this. After rewriting this expression, any problem? Yeah. After rewriting this expression, I'm going to define this one as gradient of a vector field, gradient of a scalar field T. Let me call it as a gradient. This is now a new thing for you. This may be a new thing for you, okay? But let me define it like this, okay? This whole vector as a gradient of some scalar field. Let me call like that. So dot product with, okay, that is dl vector. That is dl vector. Is that okay? Speak out. Where dl vector is equal to dx into x cap plus dy into y cap plus dz into z cap. Is that okay? Speak out. We call this one as gradient of t. Okay? Now you can define that gradient. Okay, what is that gradient? That gradient of t. T is a 3 variable function that's equal to dou t by dou x into x cap plus dou t by dou y into y cap plus dou t by dou z into z cap, isn't it? Is that okay? Now look at this gradient. This is also kind of operation actually, okay, on some scalar. And this is also point operation. Can you see this one? Because these derivatives, these are partial derivatives, right? Those derivatives are taken at some point in space, isn't it? Are you getting my point? We say we have taken gradient, okay, gradient at some point in space, x naught, y naught, z naught. That means if you take a x derivative, you put this value, you take y derivative, so partial derivative with respect to y, you put this value, you take partial derivative with respect to z, you put this value, what you get a vector. This is a scalar, okay? If you take this partial derivative at some point in space, and if you substitute those values, what you get a vector, am I right? And you are going to do that one at some point in space, just like a derivative, single variable derivative, isn't it? So this was a, how to say, point variable, or if you take derivative as operation, this was a point operation, am I right? You are going to take a derivative at some point in space, like that. You can take a gradient of a scalar at some point in space.
take the gradient, whatever we take the point, that point should be a tangent or
That gradient interpretation, don't move forward. Point is point. Point in a space, that's what I'm talking about. Any point in space. So just like if you, yeah. Why you call point as a tangent? No. This point can be anything. That's what I'm saying. Don't move forward. You are thinking about some question that you have solved yesterday, isn't it? That Txyz is equal to constant. That will represent a surface actually. And gradient is normal to the surface and all. Wait a second. Okay, I'll come to that point later. Okay. Yeah. I mean, while developing theory, okay, you should just leave all prejudice. Okay. I mean, whatever you have done, you have to develop there, isn't it? Again, that will give you a lot of insight towards the subject actually. Is that okay? Even though you know the further thing, but you should develop at that point, isn't it? That's what they did at that time, isn't it? That skill you have to develop. Yeah, speak out.
So I was saying that tangent is also the geometrical representation, I think, of derivative, sir.
Wait.
Sir, I was saying that I think the tangent is also the geometrical representation of derivative, sir.
Changing?
Tangent, sir.
Tangent. No, it was slope of the tangent, okay? I mean, again, this was slope of the, what is the quantity value? That value is the slope of the tangent actually, okay? Wait a second, I'll come to that one. So one thing you need to point out here, this gradient, this is very similar to our derivative in case of single variable calculus, but that was a scalar, but this is a vector. Okay, this is a vector. But if you take gradient as an operation that you do on a scalar, okay, so this is a point operation. You are going to do this operation at some point in space. Okay. Or if you want to take this one as a, this whole thing is a vector, am I right? If you want to take that gradient as a variable, okay, this is a point variable. This depends on a point in space, am I right? This is del t. So again, so this also x variable. Again, this also depends on x, y, z. This also depends on x, y, z. This also depends on x, y, z, isn't it? As a whole, this is a vector field actually. Gradient is a vector field that depends on x, y, z. Each of these components depends on x, y, z. Observe that one. Is that okay? Yes. Now look at here. So can I take this one as a basic definition of change in t? Okay. So when you move in a particular direction, that is given by gradient of t dot product with displacement vector. This dl vector, that vector direction is along our displacement. Is that okay? Dl vector.
So, sir, this dot product, it is like projection on the field.
Obviously, dot product is defined as projection only. Projection of dl on this del t or del t on dl, whatever. Yeah, that's correct. Dot product, again, mathematically, the same dot product I am talking about. Scalar product only. Okay? Wait a second.
Sir?
Yeah. Yes.
Sir, the gradient is a vector field, sir.
Yes, gradient is a vector field.
But the temperature is scalar, sir.
Temperature is scalar field. After taking gradient, speak up.
The field of any scalar quantity can be vector, sir.
This is not temperature. Gradient is not temperature.
Okay.
Are you getting? Gradient of temperature, that's how you say. That's a vector. That's a vector field. You can see here. This is the definition. Okay. Now look at here. Again, this may be very old mathematics for you. Okay. You might have studied in BSc or something. Okay. But if you write down and if you keep on thinking, you will have much more insight. Okay. Write down this expression. Think over it. Write down this expression. Think over it. You will generate different idea because you know about dot product. Okay. When you see the expression, I mean, look at here. That's how we say digestion. Am I right? It takes time to digest actually. If it is new thing for you, it may take more time. But if you write something or if you work out something or if you even just write and sit and think, okay, you will develop the idea, that mathematical idea actually. Okay, that's very, very important. Okay, more time we spend on this chapter, okay, less time we will spend on further chapters actually. Okay, so that I can just give you the instructions. Yeah. Now look at here. So that's why this is a vector field. You can see here. Even though it's a scalar, am I right? These t are scalars. The gradient is a vector field. Okay. Now look at here. Now, can you find the similarity with a single variable calculus? Isn't it? Here it was only one direction. You had only one direction. You don't have to define any vector. But here you can move in the infinitesimally. You can move in infinitely many direction. You define the infinitesimal displacement vector. Okay. Can you find the similarity? Is that okay? But here it is a dot product. Is that okay? But these two are exactly similar. That's in case of single variable. This in case of three variable. Now we shall talk about, look at here. Again, here we know what is this derivative. We define derivative as a limit. We know what we call geometrical meaning of derivative and all, isn't it? Now look at here. But here we define, again, we don't define directly derivative. We define some strange thing that is gradient, okay? What is that gradient, okay? All interpretation of the gradient should be on this one only. On this expression only. Is that okay? If you want to do any geometrical or any even physical, if you want to give any physical meaning or geometrical meaning for this gradient, okay? Physical meaning only when it's some physical variable, okay? If you take it as a temperature. So you have to start with this expression. Is that okay? Now look at here. Now let me start interpretation of gradient. Okay, geometrical interpretation usually you can say like this. Now obviously gradient is a vector, am I right? Gradient is a vector, am I right? If you know any vector, what do you mean by that one? That means you know its direction and magnitude. Are you getting my point? If you know any vector, that means you know its direction, you know its magnitude, isn't it? That is the meaning that you know about the vector, isn't it? Now we shall attack that one like that. Again, we shall try to interpret what is its direction. We shall try to interpret what is its magnitude. Is that okay? Again, from this expression only. Is that okay? Now look at here. Let me rewrite this expression. dt is equal to mod of del t into mod of dl vector into cos of the angle between them. Okay, suppose you have some scalar field. Okay, you have taken gradient. Okay, that gradient may have this direction. Okay, that gradient may have this direction. This is the del t direction. Is that okay? But you are moving in some other direction, dl vector. So there is an angle between them. You have taken, so this is a point xyz. Okay, this is a point xyz. X comma y comma z. Okay, you have taken dl. Again, at that point you have taken gradient that will point in some direction because that's a vector. That's a vector. Am I right? And from that point you are displacing to the neighboring point. Okay, and okay, you have defined dl vector. Am I right? So there is an angle between them, theta. I am going to call it as cos theta. Is that okay? Now look at here. If you move in different direction, usually again, as I told, as this dx is that value of dx is constant. That's what I told. Am I right? Wherever you take in the calculus. Similarly, this value of dl is also constant actually. Is that okay? In different interpretations, we don't take different value of this dl vector. Okay, it's infinitesimal and it's constant. That's how we take. Is that okay? Now look at here. So that's why this is a constant. Okay, this is a constant. Now what is variable? Theta is variable. What do you mean by that one? You can move in a different direction. You can move along this direction. You can move opposite to that one. You can move what you call so perpendicular to that one, isn't it? This is a vector drawn at that point. Okay. So when you move in a different direction, you will get different change in t, isn't it? Are you getting the point? If you make an infinitesimal displacement in a different direction, you are getting different change in t because you have cos theta variable, isn't it? Write down this expression and think over it. Okay? Because this is a constant. This is a constant. This is also constant. Am I right? This is taken at that point. This gradient is taken at that point. Mod of that one is also constant, am I right? If you move in a different direction, again, this is infinitesimal, okay? When you make that changes, xyz is not changing. We say, again, even though you make very small change here, okay, we are going to take derivative of that one at that point only, okay? Speak out. Now look at here. At that point, this is constant, okay, and this is usually constant. I mean, so throughout our calculus, just like dx, okay. So what is variable? This theta is variable. You can move in a different direction. You can have different change in t, am I right? Sometimes you can have large change in t. Sometimes you can have low change in t, isn't it? Now look at here. When this change in t is maximum, when theta is equal to 0, am I right? Speak out. Look at this expression. Look at this expression. When this change in t is maximum, when cos theta is maximum, when cos theta is maximum, when theta equal to 0 degree. When theta equal to 180 degree also, this is maximum. But in that case, dt will be negative. That means dt is decreasing, okay? But let me take theta is equal to 0 first. Later, let me interpret theta equal to 180 degree. Is that okay? When theta is equal to 0, okay, when theta is equal to 0, you have dt maximum, am I right? Are you getting my point? So that is equal to del t into dl vector, isn't it? Into cos 0. Speak out. Look at this one. Look at this one. You can just do this one. Everything you know dot product. Okay. You know about vector. Everything you know here. Okay. Yeah. Yes.
Whatever we need the dot product, del P is 3 dimension, right? D also in 3 dimension. And after doing the dot product,
You will get a scalar. Yeah.
scalar in which direction?
Scalar will have any direction?
No, that's why I'm saying in X, Y, Z.
Scalar will have any direction?
No.
No, that's what I'm saying. Dot product of two vectors, that's a scalar, am I right? As you said, it's a projection. Projection length or something, isn't it? We interpreted dot product, isn't it? After taking dot product, vector is gone. You don't assign any direction to scalar, isn't it? Speak out. Yeah. Yes. Now look at here. When theta is equal to 0, okay, that means, what do you mean by, again, this change in t is maximum. That's what I told, am I right? When theta is equal to 0, so dt is maximum, am I right? Change in t is maximum. Okay. So what do you mean by that theta equal to 0? Theta equal to 0 means you are moving along the direction of gradient. Isn't it? I got one information here. When theta is equal to 0, change in t is maximum. Am I right? So now look at it. I got one information. When theta is equal to 0, that means when you displace along gradient direction, your change in t is maximum. I got one information here. Is that okay? Speak out. Let me write like this. When theta is equal to 0, when theta is equal to 0, dt is maximum. Am I right? Now look at here.
Sir,
Yeah.
suppose theta equal to 0, del T and del L has one same direction.
Yeah, again, again, that's what I defined theta here. Look at here. This dl vector and gradient both are in the same direction. That's what I have taken. When theta is equal to 0, again, according to this expression, cos theta varies from -1 to +1. Am I right? When theta is equal to 0, this dt will be maximum. That's what you can observe. Is that okay? So that's why I got one information here. Okay, I got one information here. First information about the gradient. Look at here. Gradient. Okay, it's a vector. Am I right? Points in the direction of, or direction of gradient. Direction of gradient is in the direction of maximum increase of temperature increase of T. So T need not be temperature, okay? Can I say like this? I got 1 point from this idea. The direction of gradient is in the direction of maximum increase of, so that scalar field T. Can I say like this? I don't know, because if I make theta equal to 0, if I make theta is equal to 0 means I am displacing along gradient direction. In that case, change in T happens to be maximum, am I right? So that's why I got one idea that what is the direction of this gradient? This direction of the gradient is in the, again, the direction of the gradient is in the direction of maximum increase of T. Isn't it? That's the first idea that I can get here. Speak out. First one. Now look at here. You had a vector. Now you got information about its direction. Am I right? You had a vector, strange vector. You called that one as a gradient of a scalar, isn't it? Now you got its information about its direction. Is that okay? First one. So second one, okay, look at here. Let me take theta is equal to 0. If I put theta is equal to 0 degree, what will happen to this dt? That's equal to del t, okay? That's equal to del t mod dl vector into cos 0. That's equal to 1. Am I right? Mod into cos 0, that's equal to 1. Am I right? Now, from this one, can you solve it for del t? Remember, you have taken this one when theta equal to 0, okay? You have taken this one when theta equal to 0, when you are moving along the direction of gradient, okay? Now, this magnitude of the gradient, you got the information about its direction, okay? Now you have to think about magnitude. Magnitude of this gradient is equal to, look at here, dt by dl, am I right? So can I write like this? dt by mod dl. Is that okay? So shall I rub it out? Magnitude of this gradient, I better to write this dt as dt max actually, okay? Can I write max? Not T max, dt max actually, okay? Change in temperature is maximum, that's the meaning, okay? Not temperature is maximum, okay? That's equal to dt max by dl vector mod, am I right? As a total, look at here, if dt is maximum, okay, if the dt is maximum, dt by dl is also maximum, am I right? If dt is maximum, dt by dl is also maximum, because we kept dl constant, isn't it? So that's why, what is the magnitude of the gradient? That magnitude of the gradient, okay, it is a rate of change. This is a rate of change, just like df by dx. Look at here, isn't it? So that's equal to, that's a rate of change. Look at here, look at that mathematical expression. That's a rate of change of temperature with respect to displacement, with respect to distance in that particular direction. Is that okay? Again, remember, when theta is equal to 0, don't forget. Okay, you have taken that expression when theta is equal to 0. Is that okay? So see the expression carefully. So this modulus of this vector, okay, so that's equal to rate of change of the scalar with respect to distance. Okay. Again, obviously, this also, if you take one point in space, that's constant, that's correct. Again, this is similar to your slope actually. But what is this one? This is slope in the direction of, or what is this one? If you see this one, this is a slope, am I right? This slope in some particular direction. What is the direction? Direction is this one only, del t only. Look at this part of the expression. Now, so can you just write down the second point that you can understand here? The second point that you can understand about this gradient is the magnitude of gradient is the magnitude of gradient is rate of change rate of change of t rate of change of t again with respect to dl, okay, with respect to dl vector, mod dl vector, okay, rate of change of t in the direction of maximum increase of t. Can you write down? In the direction of maximum increase of t. Wait a second, let me complete my statement. Magnitude of gradient is a rate of change of, again look at here, I told there are different directions that you can move. In a different direction you may have different rate of change, am I right? I have started with argument that we may need infinitely many derivatives, am I right? Now look at here. Magnitude of gradient is a rate of change of t, okay? But that rate of change depends on the direction that you have displaced, am I right? This is rate of change of t in the direction of maximum increase of t, okay? If you move from one point in space to neighboring point in space, okay? Okay, if you move in a different direction, so in some direction temperature may increase in a larger extent, the largest extent, okay? In some direction temperature may not change, okay? So temperature of scalar field, okay? In some direction, what you call, so it may change by a very low value, isn't it? So there is one direction where our temperature changes in the maximum extent, am I right? If you move from this point to neighboring point, in one particular direction, that change in temperature, that change in scalar field is maximum, am I right? That direction is the direction of gradient actually. Is that okay? And rate of change of that temperature, okay, that is nothing but the magnitude of the gradient. In that rate of change of temperature, in that particular direction, in one particular direction that is changing in the maximum extent, its rate of change is maximum in some particular direction. Is that okay? That direction is a direction of gradient, and rate of change in that particular direction, okay, that's the magnitude of the gradient. So these two we obtained from this expression only, remember. Write down this expression and think over it. Is that okay? Where mod dl is constant actually, okay? Speak out.
Sir, the second point is maximum increase of t. Sir, I'm not understanding the exponent. So why in second case we are taking maximum increase of t, sir? Why is theta goes to 0?
Again, don't concentrate only on this one. In the direction of, I'm saying this is a rate of change of t, am I right? Magnitude of this one is a rate of change of t. Rate of change of t depends on the direction, isn't it? That's what I have started with. Rate of change of t, that depends on the direction, am I right? You said magnitude is a rate of change of t, isn't it? But rate of change of t in which direction? Are you getting my point? In the direction of maximum increase of t. Is that okay? Speak out.
Yes, sir.
Yes. Now look at here. So this is all about gradient.
Sir,
Yes.
we can define this in 2 dimensions also. Like
Yes. You can define gradient in 2 dimensions. You just take only a 2 part. dl also, to dx and dy only. Yeah, you can do that one. You can do the gradient in 2 dimensions. Why not? if you go from more than one dimension, it will become a vector, okay? The whole calculus becomes a vector, okay? Vector kind of calculus actually. If you are in only one direction, you don't have to take a vector that you can see here, isn't it? Yes. Now let me take one very nice physical example that most of the books quote, okay? You have one hill, okay? That hill you can just draw like this. Am I right? You have one hill here, okay? You have one hill that I have drawn in 3 dimensions, okay? This is a ground. This is a ground. You have one hill. Now, yeah, speak out.
You are writing 3 dimensions.
Yeah, I'm trying to write the 3 dimension. I can only try, isn't it? Look at here. What I can do here is, so can I just draw like this? This is a hill. X-axis, Y-axis, Z-axis. Okay. Now I want to write a function for the surface of the hill. Actually, this hill have a surface. Am I right? So now that height of that one, okay, height from this ground, that ground I will take it as a XY plane, okay? Can you imagine? I'll take that XY plane as a ground, okay? From that ground, that hill is above, okay? Now this height, so that's a function of X and Y, isn't it? Height as a function of X and Y, height of the hill. Is that okay? If you define that one, that means you define this surface actually. If you define that height function, isn't it? So height is some value at this point, height is some other value at this point. Okay, if you take different xy point, okay, its heights are different. That's how you generate that hill mathematically. Can you imagine this one? Is that okay? Now this is a height function, am I right? Height is a scalar function, obviously. Isn't it? Height is a function. You got a scalar function, am I right? Now look at here. Now, suppose if you are standing somewhere, okay? If you are standing somewhere, suppose if you are standing somewhere, okay? You again, at that point you will have some height, okay? Now, you are quite bigger compared to the whole hill, okay? That's a difference too. Now, if you look around you, okay, if you see around you, okay, so in some direction you may find more slope, in some direction you may find less slope. Suppose you are what you call doing trekking, okay? Just imagine you are doing trekking. While doing trekking, suppose you are lazy, you will find the less slope, what you call path, isn't it? Suppose if you look around you, okay, or while getting down also, you will look around the path which has a less slope, so that you can safely, what you call, get down, isn't it? So now, if you look around your what you call surrounding, okay, you will find some region where you have a maximum slope, some what you call some path, some direction. Can I say like this? In some direction you will have a maximum slope. In some direction you will have a what you call minimum slope. Okay, speak up. So again, there will be different slope in different direction. If you while climbing a hill, isn't it? Different slope in different direction, isn't it? So now that if you are pointing towards that maximum slope direction, that is the direction of gradient of this height function. That's a height function that you can define. So gradient of height function you can define. Look at here. This is a 2-dimension. This is a 2-variable function. Is that okay? This is a 2-variable function. Now gradient. It's a 2-dimensional vector. Okay. Is that okay? Now, if you look around you while doing trekking, if you look around you, there will be some direction where height will increase in the maximum way, isn't it? That is the highest slope, isn't it? Slope of that one is magnitude of this one, direction of that one is direction of this one. Gradient of height function. Is that okay? So this is one of the physical example actually. Isn't it? You have many directions to you can do trekking in many directions, but so there is one particular direction where slope is maximum, where height will change. Rate of change of height is maximum. That means that's why slope is high, isn't it? Are you getting my point? Slope is very high means height is changing. Height of that again hill is changing very fast, isn't it? In that particular direction. Are you getting my point? Is that okay? That direction is the direction of gradient of height function. Okay, and magnitude of the gradient is equal to what you call rate of change of height in that particular direction. Is that okay? Just imagine you are doing trekking and try to apply that logic. Is that okay? Speak out. And the similar idea you can find in any book. So in Griffiths also he has given this idea. Okay. So try to interpret that one. Is that okay? You will get much more physical idea. So there are some questions on this one you need to solve later. Now let me take one best example. Okay, this is what most of the book gives. Let me take one best example here. Okay, I have coordinate x, y, z here. Okay, I have origin here. Okay, I have a radial distance r. Is that okay? I have a radial distance r. And I have a radial vector r, okay, and radial distance r. What is that radial distance? How do you write? Root of x square plus y square plus z square, or distance of this point from the origin. Can I say like this? Distance of the point from the origin. Can I write like this? Speak out. Distance of the point x comma y comma z. So from the origin. Is that okay?
Sir,
Yeah.
in the previous
Hmm.
area, I mean, if I will take delta H, I mean, magnitude,
Hmm.
that will give the direction, or I mean, sorry, that will give the magnitude of the
Slope.
slope, I mean, right?
Huh.
High slope,
Again, how fast h is changing with respect to distance?
magnitude.
Magnitude gives the rate of increase of height with respect to displacement.
So then, sir, if I will go directly to the point, I mean, height to the direct.
You are moving on the surface. You are not moving in the air. How can you directly go? You have to move on the surface. Am I right?
In
Surface of the hill.
In the space, I mean, in
Huh.
the XY plane, I can point out which is the peak, I mean, peak point.
You have to move on the surface. That hx comma y is a again it will generate a surface actually. Okay, you can directly move there, isn't it? You have to move on the surface, isn't it?
On the surface. Okay.
You are not using helicopter.
Yes.
Yeah.
Sir,
Yes.
sir, in that direction, it is difficult
To climb.
go.
To climb. That's it.
Yeah.
You can think like that.
That's why we see saddle point.
The saddle point is different. The top point you can call it as a saddle point. Saddle point is different. Wait a second. I'll come to top point is called maxima. Okay. So try to solve some problem. Later I will come out with the idea. Okay. At the top point actually, again at that point usually you will have a what you call. If you take very small region of the top point, at all point you have zero slope, isn't it? Very small region of the top of the hill. Okay. If you move in any direction, you will experience no slope, isn't it? That is the point where your gradient vanishes. If you move in any direction, okay, its magnitude is 0. I mean, there is no slope at all. Top of the hill is the point where your gradient vanishes. Yeah, speak up. Now come to this question. Distance from the origin, okay? This is a distance from the origin. Now we shall take the gradient of this one. Gradient of r. How do you write? Dou r by dou x into x cap, dou r by dou y into y cap, dou r by dou z into z cap. What is dou r by dou x? 2 root of x square plus y square plus z square into 2x x cap plus 2 root of x square plus y square plus z square into 2y y cap plus 2 root of x square plus y square plus z square 2z z cap, isn't it? 2 got cancelled. The whole thing you can take, look at here, del r, that's equal to, you can take this root of x square plus y square plus z square outside, okay? You will get x into x cap plus y into y cap plus z into z cap. What is this one? R vector. What is this one? Magnitude of r. What is this one? Gradient of radial distance or distance from the origin is equal to r cap. Okay? That's equal to r cap. Is that okay? Now what is the magnitude of this one? Speak out. I hope you can do this one, isn't it? What is magnitude of this one? 1, am I right? Now look at here. This gradient of what you call distance from the origin, okay? That is in this direction. What do you mean by that? What do you mean by that? Distance from the origin. Okay? At this point, okay, you have gradient which is pointing in this direction, okay? R cap direction, am I right? Can I draw it like this? R cap direction. What do you mean by that one? That means when you move along R cap direction, what do you mean by this R cap direction? That is, you are moving away from the origin. That R cap points away from the origin. Can I say like this? Okay. Now, if you move away from the origin, distance from the origin will change in the maximum extent. Isn't it? Or if you move like this, suppose, then distance from the origin will not change much. Am I right? Look at here. If you move like this, distance from the origin will change in the maximum extent. Am I right? In R cap direction, you have maximum change of distance from the origin. Just think over it. Our scalar field, that is distance from the origin. Is that okay? Whatever a scalar field I defined, that's the distance from the origin. Okay? If you move away from if you move exactly away from the origin, distance from the origin will change in the maximum extent. That is the direction of the gradient. You can observe here. And what is the magnitude of the gradient? That's equal to 1. Why? You take displacement, you take rate of change of distance, okay, with respect to displacement, isn't it? So how do you write this one? How do you write this one actually? You are going to write this del r, okay. So that's equal to you can write dr divided by mod of dr again, because you are moving in that direction only, isn't it? That's why that became 1 actually. In case of what you call spherical polar coordinate, it will be more visible. We shall see that in a bit. Okay. In case of spherical polar coordinate, it will be more visible. Are you getting my point? You can just write. So this dr by this dl vector, whatever you write, okay. So both are same actually. These magnitudes will be same actually. Yes, this one more idea. try to grab the idea of gradient here, okay? Now look at here. One more thing. So what's the time? One more small idea. Suppose what you have done here is dt is equal to gradient t dot dl. Am I right? Gradient and its magnitude gives you the rate of change or rate of increase in the maximum direction. Am I right? Maximal direction, isn't it? Now, suppose if you need rate of change, okay, in some other direction other than the gradient direction, then what will you do? Okay, if you want rate of change in the maximum change direction of t, then you can go for gradient. You can find gradient, take the magnitude. Is that okay? That's how magnitude of the gradient is defined, isn't it? Now, suppose if you need rate of change of that scalar field in the direction where that's some other direction, some other arbitrary direction, then what will you do? Isn't it? Suppose if you need rate of change in some arbitrary direction, not in the direction of gradient, not in the direction of maximum change of t, okay? So then what you can do here is, look at here, this dl is any arbitrary displacement. We can write like this, del t. Is that okay? Del t. What I do is I'm going to define, suppose this is my point x comma y comma z, okay? So this is my dl vector. I'm going to define a unit vector along the dl vector direction, okay? dl vector divided by mod dl vector. I'm going to define a unit vector. Is that okay? Along the direction of your displacement, define a unit vector. Is that okay? So now, dot product with, what is dl vector now? That's equal to n cap into mod dl vector. Can I write like this? N cap into mod dl vector. This vector, I have written it as unit vector into its magnitude. That's it. Is that okay? So dt. Now, if you take this dl here, now can I write like this? This is gradient of t, okay? So dot n cap, okay, dt by dl mod dl. What does this dot product gives? This dot product gives the change in t if you move in different direction. Am I right? I need a rate of change of t, okay, when I move in arbitrary direction, isn't it? So then what I did is I replaced this one like this, or you can do like this. In this whole expression, you can do like this, dt divided by mod dl. That's equal to del t, so dot dl divided by mod dl, some n cap unit vector along dl. Can I write like this? Divide this whole expression by mod dl. Okay, so this will give rate of change of t, okay, with respect to distance only, okay, rate of change of t with respect to distance when you move along n cap direction. Can I say like this? We call this as directional derivative. We call that as directional derivative. Is that okay? Directional derivative. Wait a second. So now, or you can write in other way actually. You can write in other way. Suppose if you know the angle. So I hope you got this point. Suppose if you know the angle, can I write? You can write like this, isn't it? Into dl vector into cos theta. Am I right? dt, isn't it? You can write like this. Then you can write dt divided by mod dl. You can write like this also, del t into cos theta. So these two are same actually, isn't it? Mod of this one into cos of the angle between them. We call this one as a directional derivative. That means you have a gradient. If you have a gradient, okay, if you take dot product with some unit vector, okay, that unit vector points in some direction in space, okay? Then what you get is, you get rate of change of this t along that particular direction. Rate of change of t with respect to distance when you move along that particular distance. So look at here. Here I have taken dl, am I right? Here I have taken dl. Wait a second. I'll give the best analogy here, okay? I'll give the best analogy. So del t, dou t by dou x into x cap plus dou t by dou y into y cap plus dou t by dou z into z cap. Can I write like this? Okay. Now let me take dot product with del t. Let me take dot product with x cap. Is that okay? Let me take dot product with x cap. What would you get if you take dot product with x cap? You will get dou t by dou x. Your partial derivative is a directional derivative actually. It is a rate of change of t when you move along x-axis, when you move along x cap direction. When you move along x cap direction, what do you mean by that one? You are keeping y and z constant, isn't it? Is that okay? So that's why these partial derivatives are actually directional derivative. Is that okay? So wait a second. Similarly, del t dot y cap. How do you write this one? Dou t by dou y. Like that you can go for z, isn't it? Speak out. So this is actually directional derivative. Or you will get rate of change of t with respect to distance when you move along x-axis. You will get rate of change of t with respect to y, okay, with respect to distance when you move along y-axis. When you move along y-axis, only y changes. When you move along x-axis, only x changes. Is that okay? So similarly, if you move along n cap direction, can I write it like this? Dou t by dou n. Actually, this whatever dou n I have written, that is similar to this one only, okay? But I have written that one because to generalize this one, okay? And we are going to use this one somewhere later, okay? We call this as directional derivative. So let me assume this n is some translational coordinate along n cap direction. Can I say like this? This in place of dl I have put dou n or something. That is the only difference that I did. Is that okay? Where n is some coordinate along n cap direction. Let me take it like that. Is that okay? So we call it as directional derivative. Okay? Have that idea. That's also required. Okay? Now look at here. Gradient helped us to find derivative in any particular direction. Look at here. I told there are infinitely many derivatives exist. Am I right? From a point you can move in infinitely many ways. And there are infinitely many derivatives may exist. There are infinitely many rate of change may exist. Am I right? Now look at here. So any particular rate of change you can obtain from gradient. Gradient helped us, and again in all ways, isn't it? Speak out. You can choose an n cap in any, how many n cap that you can make? Infinitely many, from some point to some neighboring point, isn't it? In space. Look at here. All of those, that infinite number of derivative, whatever I told, look at here. That is given by this expression. Is that okay? That's how our gradient simplified the mathematics, isn't it? Can I say like this? Yes, you can solve problem number 1.11, 1.12, 1.13. Okay. Don't think that you will solve tomorrow. Okay. Tomorrow, again, this number of problem in the beginning, it will be always less only, isn't it? Whatever the topic we have discussed, whether quantum mechanics, isn't it? Later it will increase. It will increase exponentially, but it will saturate somewhere. Okay. Don't worry. But it will increase. Okay. So you may have only 3 problems. Maybe tomorrow you will get 5 problems. Okay. If you leave this 3 problem, that if you, you may think that I will solve tomorrow. Tomorrow how many problems you will get? 8 problems, 10 problems. Okay, solve today only. Problem number 1.1, 1.11, 1.12, 1.13. Okay, let me mention in the homework. You have a temperature as a variable, spatial variable, am I right? From a point in space, you can move in infinitely many directions. If you move in different direction, rate of change of temperature is different. Rate of change of temperature with respect to distance. Okay. Suppose if you want to move in some arbitrary direction, what is the rate of change of temperature? That is given by this dot product of unit vector with the direction.
Okay. Any arbitrary direction?
No. Yeah. In any arbitrary, the n cap is arbitrary here. I define n cap as arbitrary.
Which I will prefer in the direction. I can zoom it.
Yes. If you move along gradient direction, you will get maximum change. But if you move in some other direction, you may not get maximum rate of change. You may get some other rate of change, isn't it? And what is that rate of change? What is the value of that rate of change? That is obtained by this directional derivative. Okay? And I need this one.